Perfect. So this is congratulations on making it to the end, and thank you for staying to watch. You might notice this has a slightly different title to what's on the program, and that's because some amount of intervening time, we came up with this notion of weaving the digital tapestry. I'll talk more about that as we go. Yeah, so this is a talk about emulating cohorts of digital twins using Gaussian processes, and I'll kind of be focusing in on cardiac models. So this is a piece of work done between Nottingham and Imperial with Cristobal, Abdul, Steve, and Rich. And so I'll be talking a little bit about what a digital twin is, defining it, and talking about computer model emulation and when you might want to use computer model emulation for your digital twin. Then we'll talk through our motivating example, which is this cohort of cardiac digital twins. And then I'll talk a little bit about the cohort learning methods that we've been working with and show you some results of what we've got so far. So digital twins are one of those where pretty much everyone you talk to will have a slightly different definition. But sitting at the core of all of that is that a digital twin is an in silico representation of a real-world object, usually encoded into kind of a mathematical or a computer model. And then the real-world object and your digital twin are in some way connected by data. Hopefully passing in both directions. And so kind of potentially the most frequently used, or the digital twin, is Google Maps, arguably a digital twin of the surface of the Earth. Google Maps, it turns out, has 1 billion monthly active users, so I think it's probably more than any of us could ever hope for our code to get looked at by. And so here's me querying our digital twin, trying to work out how to leave. And potentially, on my way, I'd like to get a very good coffee. I don't know if anyone's been to Federal on the way between here and the train station. It's very nice. But here, well, this would have made more sense when my talk was going to be at 10. If you'd wanted to leave my talk to go and get a coffee, it would have been busy, so I'd have encouraged you to stay. As it is now, you can leave at your leisure. But yeah, so when we talk about that kind of passing of data between the digital twin and the real world, Google obviously is collecting a load of data on its own, but it's also now asking you, and it gives that out to the user in terms of like how long it takes to get somewhere, whether there's traffic. But it's also, I don't know if you've noticed it, when you're using Google Maps, if you get on a bus, it will say how busy is the bus right now, and that's it collecting data from you so it can then pass that on to other people as we go. Digital twins that we might see a little bit more frequently in kind of our work in academia, so personalized cardiac models, which we'll talk about a little bit today. So these are kind of precision medicine models where you have a patient and you take some kind of scan of their heart, which gives you this like personalized mesh, and which is your kind of digital twin object. And then you can use that to kind of guide treatment or do prognosis for patients. Quite a lot of digital twins in industrial settings, used to kind of optimize things like maintenance schedules, check when things are going to break. And then obviously energy, quite a good space for digital twinning. You can kind of predict surges and optimize power distributions across cities. But what we're kind of talking about here, right, this kind of creation. So I guess actually maybe we should talk a little bit about like the distinction maybe between a digital twin and a model. That's a real blurry line, and some people will get mad at me and just be like, a digital twin is a model, don't be silly. But the way I like to think about it in terms of, maybe in terms of hearts, right, is the digital twin is we've got this personalized mesh, we then model the beats of the heart, and like, that's how we look at an EKG. Whereas like for a model, you might literally just model the EKG, you might just do the time series. I think it's that kind of, having that object is the thing that is the distinction between the two. I mean, arguably a digital twin is just a subset of modeling, but yeah. But to do that, right, that's a lot more information. Modeling a whole heart's way harder than just modeling an EKG trace. In terms of like the number of mathematical things you have to do. And so these kind of models can be computationally expensive. The things that my collaborators are working with are kind of, I think 1 beat of the heart takes a day on Archer, which is the most powerful HPC in the UK. And you ideally want models that run faster than that in general. So in those kind of cases, you use emulators or surrogate models. And there's kind of quite a lot of options for those. So one is that you just simplify your mathematical model. So you can linearize, or you could use a process like symbolic regression to like learn a simplified version of your mathematical model, still in like expressed mathematically. Then the other option is kind of moving towards statistical or machine learning models. So you could do a kind of regression emulator, or if you want something like a little bit more fun, you do a Gaussian process emulator, which is what we'll obviously be talking about today. So I've talked a little bit about why you might want them, but the kind of times in which they're useful, and so fast-paced real-world settings. When you want to know something really quickly, So if you're looking to do clinical recommendations on someone who's in heart failure, you don't want to go away to Archer and spend 3 days simulating their heart. Or if you're working in kind of structural health monitoring, if you're an engineer, you probably don't want to spend ages working out if your bridge is going to break like tomorrow or in a week after you've done your simulations. And then on the other side, it might just be that you want to do something that's mathematically, computationally intensive in its own right. So something like sensitivity analysis or parameter calibration often requires loads and loads and loads of runs of your simulators, and it's way, way easier just to do loads and loads of runs of your emulator. So here we come to this notion of weaving the digital tapestry. So in some cases, you might have a kind of cohort of digital twins, so loads of models of objects that are relatively similar. Lots of planes, lots of buildings, lots of hearts. And you kind of you might want to use all your knowledge you get from these simultaneously. So outlier detection. Have you got a patient who's ill? Have you got a car that's going to break down? Have you got a building that's actually performing way better in terms of energy consumption? Can you learn something from that? And so you might be using it for that. The other option is something like in silico trials. Does anyone know about in silico trials? Vaguely? No? Some nods? So the idea here is that instead of doing kind of invasive trials on like an actual, like medical trials on an actual person, you do it on a big group of models of people. So then you can kind of do things that might be dangerous or kind of ethically unsound, but to computers and not to people, to kind of test whether an intervention might work. And as I said, with digital twins, you might actually want an emulator or a surrogate model to help you along the way in that. And traditionally, for these kind of models, or these kind of cohorts, emulators have been trained individually for each individual cohort member. But we believe that if the underlying real-world structures are sufficiently similar, like most hearts are kind of the same, they're topologically quite similar, they beat similarly-ish, kind of up to disease, I guess. It should be possible for any new emulator you add to the cohort to learn from your previous emulators, to kind of gather cohort knowledge, as it were. And so our kind of aim is, if we've already got a cohort of emulators and we want to train a new one, we want to be able to train that new one on significantly fewer training points than it took to train the original ones and still get the same kind of predictive accuracy. So this is just like a little bit of notation. So what is making up our... Oh, and the reason we're talking about weaving the digital tapestry, sorry, I have to keep remembering to say this, is that we're conceiving of these digital twins as, in fact, as digital threads that we weave together into a tapestry of knowledge. Yeah. I didn't write the grant for that one, but so yeah. So what makes that? What do we need to kind of create our cohort of emulators? So we have a group of n real-world objects, which I'm calling O for object, and then these objects are going to differ from each other in some way according to some set of latent variables. So where for object n, Ln is the set of variables that describes it uniquely compared to the other object. So that could be, in some cases, you might know that explicitly. You might know that one building is in a location that's always got a kind of steady temperature of 20 degrees, and then your other building's got a steady internal temperature of 18 degrees. So that's like a thing that determines the difference between the two, but wouldn't necessarily be a parameter that you're varying in your models when you're just modeling one of them, if that makes sense. On the other hand, you might not have any kind of straightforward representation of these. So what we're going to talk about today is hearts, and each patient has an individualized mesh. So the latent variable there is the shape of the heart, but we don't necessarily have a straightforward way of describing that. But there are potentially ways to learn them. And actually, Ruby talked a little bit about that in her talk, is that learning latent variables. So then after your real-world objects, you want your digital twin, which I'm calling F here. So that a digital twin of object n is given by this function f of theta and the latent variables. And then you want an emulator for f, g, g for Gaussian process here, if you hadn't guessed, so that f equals g plus some small, usually normal error. And then if we add an n+1th member of our cohort, we want to be able to utilize our knowledge about the previous members to make emulating fn+1 faster and more computationally efficient. So what our kind of focus here today is this cohort of cardiac digital twins. So we have our real-world object, which is our patient, our digital twin, then the emulator, and then this green arrow that I've made in PowerPoint is to represent cohort learning methods to bring us faster to our final emulator. So our cohort is 18 patient-specific meshes generated using CT imaging. Hello.
Sorry, what exactly do you mean by emulating? I'm getting a bit confused. What's the difference between that and a digital twin?
So the digital twin is the mathematical model, and an emulator is an emulator of that model. So trained, like a Gaussian process of that, like trained on that model, outputs and inputs.
Why do you call it a Gaussian process?
Because so a Gaussian process is a type of model, and in this case, we're using a Gaussian process to emulate a computer model. Does that make sense? Cool. And also, it might not be a Gaussian process that you use. In our case, we're using Gaussian process emulators, but they're not like it's not necessarily that. Yeah. Yeah, no, well, it always would be a Gaussian process, obviously. So we have 18 patient-specific cardiac meshes. So these were generated using CT imaging, and then kind of that mesh gets created through a kind of computer learning process. Our simulator is the reaction iconal model of electrophysiology, and our latent features are outputs from a statistical shape model that's been designed to describe each mesh individually. If you want details on the cohort, it's in Cristobal's paper from 2021, but I'm going to talk a little bit more about how each bit of it works here. So the CT scans were taken for each patient and then converted to these personalized cardiac meshes using an image segmentation process. And this generates these personal cardiac meshes for each cohort member. This is cohort member 2. I've labeled the atria and ventricles, which are the like top and bottom bits of the heart, because they're going to be a bit important later, like notionally. And then so our simulator, we're using this reaction iconal model of electrophysiology. The way your heart beats is governed by the movement of electrical, propagation of electrical waves across the surface of your heart, and the reaction iconal model models that. Our outputs of the model are the activation times across the heart. So that's how long the electrical wave takes from its point of origin to the point on the heart. And yep, I left myself a reminder here to show you a video, because I did this in Beamer, so I can't put videos into it. But this is a visualization of the reaction iconal model propagating those waves across the heart surface. Cool. And then I have to go and do this, sorry. So the simulator outputs then, like I say, are these activation times. So that's time from origin to where you are on the heart. And then we actually simplified that down into the total activation times. So that's the time from the start of the wave to the end of the wave, like when it hits the last piece of the heart. And then we separate that between the ventricles and the atria. So we have the total activation times of the ventricles and the total activation times of the atria over our two simulator outputs that we care about. And this is the total activation times over, I think, mesh 4, just for like 3 different sets of parameter values. And we've got 6 parameters, so we're in a 6-dimensional parameter space. The conduction velocities are the kind of speed at which electricity moves across the heart. And then the 4K parameters are anisotropy ratios, which essentially tells us that whether or not that wave moves faster or slower depending on where you are in the heart. So in the fast endocardial conduction layer, you move faster than if you're in the Bachmann bundle, for example. But don't worry too much about the anatomy. I don't. Hello. I don't know, is my answer to that.
I don't think it is in that model.
It's not in there.
We've got more complex models. In this model, we're trying to do mechanics as well. So if we have models that are more complex electrophysiology, we tend to use a fixed mesh, so there's no mechanics. But yeah, so in this, I don't really think we're actually doing.
No, sure. Hello.
Are these parameters identifiable?
So I think some of them maybe are, but mostly these are taken from literature. And then what we're generally, so the kind of, once we've got all the emulators working, the idea is that we hope that we can calibrate to these parameters from patient data. In terms of the sensitivity analysis, the 2 conduction velocities are the most important by like a long stretch. And so far in the calibration, you can generally get 2 of the conduction velocities and 1 of the Ks, and the rest essentially go to prior. So to some degree. Does that answer your question?
Yeah, I mean, I just wonder, when you build an emulator, would look for the inverse problem?
Yes. So, I mean, that is one of the difficulties for the inverse problem for sure. So, in the kind of larger kind of setup for when you're going from all the way from electrophysiology to heartbeat, there's something like 140 total parameters, and the part of the process is to use GSA to reduce those. And this is kind of, I think this is like halfway through the GSA reduction is when we get to these 6 for this model, essentially. And so then the latent features for these, like I say, these are features that... Oh, actually, are there any more questions before I talk latent features? No? Sick. Good. So then the latent features come from this statistical shape model that describes the variance between the meshes. As far as I understand how that works, essentially from the 18 meshes, Cristobal worked out where the location of an average heart would be, and then all the hearts, the actual hearts get described like by vectors in their relationship to the average heart. They then performed, and then that kind of describes your heart in an array of real numbers, or what we're calling modes. They then applied a principal component analysis to that to determine which modes contributed most to the variance in the hearts. And the first 9 modes capture 90% of our explained variance. So we use those first 9 as our latent features. So a little summary of our data. We've got 18 meshes, 180 simulations per mesh. That's varying our 6 input parameters. We've got 2 outputs. That's the total activation time over the ventricles and the atria. And we've got these 9 latent features, mode 1 to mode 9, which uniquely describe each mesh. I promise this is not an intro to Gaussian processes, but just a little bit of what we're using. So for our kind of basic Gaussian process, we're using a linear mean function. We haven't talked a huge amount about means over this week, but a linear mean is essentially the equivalent of performing a linear regression and then adding a zero mean GP. But you learn everything all in one go. Yeah, you treat your regression coefficients as part of your hyperparameters, essentially. And then for our kernel, we're just using a multi-dimensional RBF, because they're nice and smooth, and that's easy. We've implemented it to, if we want to use other kernels, we can, but so far it's been fine with the RBF. And so then our baseline for how we assess how well our emulators are doing, our emulators of our simulator, is just you make an emulator per mesh. Each patient gets an individual one. You just kind of train your Gaussian process as you would in any other scenario. And so then for our first method of kind of trying to learn from the cohort is we thought, again, very simply, what happens if we just teach the Gaussian, we teach one big Gaussian process about all of our cohort members. We give it the latent features. And so for this, we concatenate our normal parameters and our latent features. So we're now in a 15-dimensional parameter space. And we just teach one big GP all of that information. So that means that the parameter inputs that you're putting in kind of looks like loads of varying and then like one big block of latent features per cohort member. They all concatenate together. Does that make sense? Yeah, vaguely. Cool. I've got one nod. That'll do. And so yeah, here when I use, so when I'm using the kind of comma notation, so f of theta and L, the implication there is that f doesn't like explicitly know L, but when you've got a semicolon, then I'm saying I've like smashed the 2 data sets together, essentially. So the proposed advantages of this kind of big latent feature emulator is that if we know enough about the latent space, you might never need to train another emulator for when you add a new cohort member, if we've already kind of covered enough of the latent space in that single emulator. However, it does require you to know or learn the latent features. So in this case, I'm really lucky that Cristobal had already done the statistical shape model. But if you've got another data set with a different set of meshes, then you have to learn something new. And also, as we know, as your training set gets larger and larger, your GPs get more and more unwieldy to train. You're more and more likely to get non-positive definite covariances, those kind of things. And so then the key idea that we're using here is this idea of the discrepancy emulator. So we say, what if we've got our first member of our cohort, F0, and we want to add a new one? What if our new one is like F0 plus a little bit of discrepancy? You might notice that this looks quite a lot like the kind of multitask idea. So we have a weight, A, and some discrepancy term. And we want to say, OK, so then if we're saying that's true, we can say the same is true about our emulators. So our new emulator is going to be kind of a weighted sum, well, just A times our old emulator plus this discrepancy term. And we'll also say the discrepancy term's a Gaussian process, because we love to say that things are Gaussian processes. And then you define your Gaussian process via a mean and a kernel. And also, just to mention that this is a method that doesn't require knowing those latent features. And so, as this is just a sum of Gaussian processes, our new emulator is also a Gaussian process, where you just have to learn the hyperparameters for m delta and k delta. But then we thought, once we'd done this, we had a kind of a little bit of success. And then we thought, oh, but what if we said, actually, our new emulator is a sum of all of our previous emulators? So we get this weighted sum over the old emulators, plus this discrepancy for the new one. And now you need to learn the discrepancy emulator hyperparameters, but you also have to learn this set of AN. So we kind of had a few thoughts about how to do this. I mean, one is that you just say, I've actually got loads of prior knowledge, and I know that my new cohort member is really, really similar to like the third one. So we'll just set that equal to that one not equal to 0 and learn it, and we'll set all the rest of them equal to 0, essentially equivalent to that single emulator case. Similarly, if you've got that big prior knowledge, you could choose a subset where you learn A. But this is based on kind of knowing a lot about what it is you're working with. Obviously, you can do it statistically, so you just you treat this set of A's, as the set of weights, as a hyperparameter and learn it during your training. But that, potentially, if you've got a massive cohort, then you've got a load of hyperparameters to learn. And so as like a kind of small hack, we were like, does people know what lasso regression is? Yeah? We're not all across the room. Anyone want me to explain it? No? Cool, great. Essentially, we thought, oh, if we use lasso regression, we can reduce our subset, which means we reduce the number of things we have to learn. And so either you could learn those weights just by lasso regression and pass those values in, or you could use lasso regression as an indicator function and then learn those non-zero weights as hyperparameters. So then, just to summarize the kind of 3 sets of models, individual emulators, which are just trained on the inputs and outputs of our simulator, and then give a new emulator with the 2 outputs. The latent emulators, which are trained on the outputs of the simulator, but also on this concatenated 15-dimensional data set. And then the discrepancy emulators, where you give it the inputs and outputs of your simulator, but you also give it the previous means and covariances from all of your previous emulators. And again, the outputs is these 2 emulators for your ATAT and VTAT. And so just to go through the results. So this is training. So I split the data on an 80-20 split, and this is training for each mesh, just training on all that data and then testing on the test data. We're using R² as a measure, so the closer you are to 1, the better your prediction. And pretty much for every mesh, we're above a 0.99 R². For most of the meshes, we're kind of hovering around 0.97-ish for VTAT and about 0.99 for ATAT. And you actually see as our number of training points increase, we get, say, 0.999 at 140 training points and 0.997, and then, as you expect, kind of decreasing before that. Which kind of tells us that this is a relatively easy problem for the emulators. We're doing really, really well. That's a high predictive accuracy from not that many training points if you look down at kind of like 80 or 60 for what is like a pretty high input dimensional problem. But we were like, we can probably still improve this. We can probably still use less of those expensive simulations to get there. So then for the latent emulators, they were trained using 17 out of the 18 meshes and then tested on test data from both the meshes that were left in and that one that was left out. And the results that I'm about to show you is that the results from that averaged over all of the 18 different latent emulators we trained. So this is just showing the results on the left-in meshes. So as your number of training points go up, so does your accuracy, and we're kind of meeting that accuracy that we were seeing for the individual emulators at about 800 training points, but that's essentially at 47 training points per cohort member, if that makes sense. However, so when I remember I said earlier, I was like, the idea of this is if we've covered our latent space, we should be able to predict really, really nicely for unseen meshes. Unfortunately, that's not so true. We do okay. We do better for VTAT than ATAT. And we're above like a 0 R-squared, which means we're predicting better than the mean. But we're not anywhere near that kind of same predictive accuracy we were talking about before. And when I kind of couldn't work out why, so I went and looked at the individual emulators, and it's because 4 absolutely tanks it. Something about Mesh 4 made it really, really hard to predict the ATAT from those latent features. I've been trying to work out why. All the methods that I have employed so far have not told me. So then, for the discrepancy emulator results, we're at the point of having about 7 different models. So I tried loads of different ways of choosing A. So I've just tried to summarize them here. I'll try and keep them all in head. So our baseline is obviously the individual emulator. Then we did an emulator with a single reference and just set A equal to 1. So we essentially said our old emulator describes the mean behavior entirely. Then we chose a single reference and learned A via regression. Then a single reference and learning A as a GPE hyperparameter. Then for the full cohort reference discrepancy emulators, we learned the whole AN set as GPE hyperparameters. Then we learned them via lasso regression. And then finally, we learned them via lasso regression, but then used the output of that as an indicator function to only learn that reduced set as hyperparameters. Whereas that's a lot of information very quickly. We're mostly going to end up talking about the last couple because they do best, so don't worry too much. But these are our results. So I don't know, that might be very hard to see at the back, I'm sorry. But the blue line there is our single emulator. And then the other lines are all of our different discrepancy emulators. And apart from at very low training set sizes, discrepancy emulators always do better than our reference. And then obviously it gets really hard to see how that's going at higher numbers. So here it is for higher training data, and we continue to do better. But that's kind of what you'd expect. We've given it more hyperparameters to play with. We've also given it loads more information. And we kind of expect hearts to be relatively similar to each other. What we actually care about is whether or not this is doing better at kind of depending on how many training points we give it. So here we are at m equals 20, m equals 40, and m equals 60 training points. And you can see that at m equals 60, we've matched the, so when I say IE equivalent, that's the individual emulator equivalent performance. And so at m equals 60, we've matched the equivalent performance at 140 training points for the single emulator. At m equals 40, we've matched at m equals 100. And at m equals 20, we've matched at m equals 50. So we're essentially more than halving the number of training points we need to achieve a similar accuracy to individual emulators. I have sped through this, but it's the last talk, so I'm hoping you're all happy about brevity. So we've kind of developed and tested 2 kind of simple methods for cohort emulations of digital twins. We had this latent feature model, which I've mistyped, but we were hoping that it might replace the need for training any future emulators. And there's potentially a bit of joy in that if we can work out what's going wrong in Mesh 4. We'll have to go there, but like I say, it suffers from some inconsistency. And it also requires you to know what those latent features are and have some expression for them. And then the second method we've tried is this discrepancy emulator model, which learns directly from the means and covariances of our previous emulators, utilizing those nice properties of Gaussian processes. And we found that in this particular problem, it halves the number of simulations required for equivalent accuracy. I think it performs similarly on a different cardiac model that I've tried. It doesn't require any knowledge about those latent features. And though it is more but on the kind of downside, it is more computationally expensive than the latent model to add new cohort members to it, because you are having to do that each time you get a new patient in. Yeah, thank you so much for listening. Does anyone have any questions? Hello.
You said at one point your dimension gets really big, right? So how do you handle the computational blow-up of that?
Oh, well, when we get to the 15, you just wait longer for your laptop. So kind of what happened was that when you hit about 1,000 training points on that 15-dimensional, the covariance matrix started breaking GPyTorch. But because it kind of didn't matter because of that left-out score just not improving. So there's probably work to do on kind of, there's probably some experiment design there where you could select better from those 800 training points. At the moment, we're doing it randomly and repeating that randomness like 10 times. But definitely, you could probably get to fewer training points again if you did some like experimental design in there. So that makes sense. Yeah, yes. Yes.
So is that a good sort of way to combat the sort of curse of dimensionality?
I mean, I guess it might be. Have you looked? I don't know. Have you looked at ways of sampling from that lattice, like even just like maxi-min or something, just to, or do you need to have it be like retain that structure?
I get a prediction over the whole thing every time, and I can like show that iteration to iteration.
Okay.
So I guess I don't do the whole thing.
Yeah. I think then, yeah, maybe kind of finding some way to sample that subset would be useful. I mean, I think part of the reason this doesn't do very well is, like I say, when you're doing that latent feature emulator and you've concatenated two matrices, you have got these massive. So for each thing you have from a single cohort member, right, you've got 6 varying ones and then 9 that are just the same. So it makes it quite easy to have points that are really, really close together, which is what messes with the covariance functions, I think, as you increase like the number going into that. But yeah, no, I think sampling probably is a good way of thinking about it, or at least like distributing over the mesh somehow. Yeah.
Well, I would say if you don't have the lattice, then how do you choose where to? That's one thing that confuses me.
Oh, so these are. So we know we've got priors on the. We've got priors on all of the parameters, and they're Latin hypercube sampled. Yeah. Just in that 6-dimensional cube, essentially. Yeah. Any other questions?
How did you set the priors for location between
So that's all done by Christabel in that previous paper, but I think mostly it's, so this is like one of the ongoing kind of like parallel things, is that mostly they started taking them from the literature, and then they created some emulators to run history matching, where they got rid of areas that produce non-physiologically sound results, essentially. And then I don't know, actually, if this has taken the results from that. This might just still be the selections from the literature. So there are potentially physiologically unsound ones within these emulators. Yeah.
And the first level of discrepancy you considered, is it, what does this discrepancy actually account for?
So I guess, so we're just on a kind of with a single reference, or with all the references? So I guess just, both kind of mean and covariance difference from the other half. So, I mean, you could argue that it's accounting for the difference in mesh shape. I mean, yes, I mean, essentially the difference in mesh shape is what it's accounting for.
But don't the mesh features account for that as parameters?
Oh, they're not in, so in the discrepancy model, they're not in, it doesn't know anything about them, because you're training them individually, so there's no need, if that makes sense. Yeah. Hello.
Had a bit of a flavour of some of the stuff that Rupi was talking about a little bit. Have you thought of any sort of clustering, or like finding a smaller number of like representative parts that kind of act as a basis function for other people's? Or? Yeah.
So before we got into the discrepancy stuff, I was trying to use the latent features to and like a distance measure between them to see if like you could better emulate, like can you better emulate mesh 2 with mesh 1 or mesh 3, essentially. And the answer seemed to be no. It didn't seem to make very much difference. But that, so essentially what this kind of is, right, is like a fast hack on multitask processes. We're not getting that kind of cross-covariance term, but we are just like learning from what we know already. And to some degree, using that kind of lasso as indicator function, that's like creating a cluster in its own right, if that makes sense. But we almost certainly could be cleverer, yes.
It kind of is the like, co-visualization model.
Yes. Yeah, quite similar. Yeah.
Do you have any more questions? Can we escape early? Okay, cool.
I think we can escape early. Thanks so much.